Hello and welcome to the web series ZeroPM Pieces. My name is Sarah Hale and I'm the project coordinator of a really exciting new research project called ZeroPM. In the ZeroPM Pieces, the researchers in the project will tell you about one piece of the ZeroPM puzzle that they're working on. So without further ado, here comes a ZeroPM piece.
Hi, this is ZeroPM piece number 6, a short talk about sustainability assessment. In the ZeroPM project, we're trying to solve some environmental problems without making other problems worse. This calls for a holistic approach to sustainability assessment. Happily, there are many possibilities for how to do this, which can be adapted to the particular needs of this project, but even this adaptation presents challenges. Environmental science is rich with acronyms. PNECs, LOLs, NAPLs, and environmental systems analysis is no better with its GWPs, QRAs, and many more. In places I teach, I'm frequently asked for a glossary to help students understand all the many acronyms that are thrown at them. So what I'm going to do today is just focus on the 3 acronyms which are the main focus of Chalmers University of Technology within the ZeroPM project. Chalmers is mostly working in Work Package 2, where all 3 of these are relevant, but also in Work Package 7, where the latter 2 matter. In the ZeroPM project, we want to eliminate persistent and mobile substances. At the same time, we have to think about what the alternatives to these substances are, because it's no good eliminating a substance if the consequence is that we generate a whole lot of some other kind of pollution. There's a name for that, and it's regrettable substitution. Chemical alternatives assessment, or the substitution of hazardous chemicals, is the use of alternative assessment methods for finding safer and environmentally preferable design options that reduce or eliminate the use of hazardous chemical substances. Safer alternatives to hazardous chemicals may simply be other chemical substances, or this may involve deeper changes in material or product design. The slide I'm showing you now is a simple way to show how the concept of essential use and the idea of chemical alternatives assessment connect. It's a way of thinking for people designing products like clothes or cosmetics or domestic goods or any other product with a recognizable function. So the first thing we should be asking ourselves is if we can eliminate problems by just reimagining the products where the problematic chemicals are used. Obviously, if there are no chemicals of concern in the product, we get out of this flowchart very fast. There are also going to be cases where a product contains a chemical of concern, but it's not strictly necessary to its function. Does your raincoat really need oil repellency if the point is to keep out the rain? No. And that's part of why we don't use fluorinated chemicals in ordinary raincoats anymore. Problem solved. But there will be cases where this may be a safety aspect of a product. For example, in some industrial settings, oil repellency might be a matter of life and death in an accident. So if the function of the chemical is essential, we should ask ourselves if there are any alternatives. Now, perhaps there are none. In that case, we should continue to use it, but provide incentives for the development of alternatives. Or perhaps there are alternatives, but none of them are exactly fantastic. This is a frequent situation where we're forced to select the least worst alternative. So what factors should we consider in chemical alternatives assessment? Life would be relatively easy if it was just a matter of hazard assessment. But sometimes inherently hazardous chemicals can be managed safely, resulting in very little exposure for the environment or for people. Both of these 2 first dot points here are typically considered in quantitative chemical risk assessment, and ideally they would be a part of chemical alternatives assessment also. We should also be thinking not just about whether the chemical is emitted in the use phase. For example, is the waterproofing chemical lost from the raincoat when it gets rained on, but also whether the chemical is emitted upstream, for example, in a factory in China where the raincoat is made. And the environmental issues are not limited to chemical toxicity. An immense amount of energy and greenhouse emissions are associated just with the spinning and weaving of textiles. So other non-toxic emissions like carbon dioxide need to be considered, as does the lifespan of the product. How much use will we get out of it per kilogram of emissions? It's possible that a chemical that we're not particularly fond of actually results in a lot of other environmental damages being reduced because the product lasts longer. And let's not forget that while some products might be interesting from an environmental point of view, they might not be feasible at large scale, or they may be prohibitively expensive and therefore only of academic interest. So this was me going through chemical alternatives assessment in 2 slides. Now I want to segue to life cycle impact assessment. There are various methods for getting data on each of these 5 points on the screen here. Regarding the first 3, one popular but challenging approach is called environmental life cycle assessment. It's used all over the world for all sorts of questions, but it's considered pretty challenging when it comes to the assessment of chemical impacts. So I'll say more about that now. Life cycle assessment is a 4-step process, of which life cycle impact assessment is one. So let's go through those 4 steps to see where this fits. The first step in an LCA, according to the ISO standards, is the definition of the goal and scope of the study. This basically means trying to identify the important unit operations involved in making a product or a service, indicated by the little tinier yellow boxes in that figure there, and also mapping out the flows that connect them. We draw a system boundary around that, the hard black line there, to identify what we're studying and what's excluded from the study. Now, once we've defined our goal and scope for an LCA, comes the time-consuming activity of life cycle inventory analysis. That's where we take this outcome of the first step, but we look at all of the flows transgressing that hard boundary, all of the energy and raw materials that go into the system, and all of the emissions that come out of the system. And this results in big long lists in most cases. But that's still not really environmentally informative information. So we have a 3rd step here called life cycle impact assessment. And that's where we take these lists of flows and we typically multiply the values in them by linear factors that express environmental impact. We call these characterization factors. So in that way, we're able to reduce a large number of emissions into a few interesting impact categories, like climate change, for example. There's a 4th step here, which is interpreting all of that data and what it means, and potentially trying to improve the system by going back to the start and redefining it, maybe putting some different unit operations into the system and finding out what the bottom line is from the life cycle impact assessment for that change system. So this is life cycle assessment in a nutshell, and it shows where life cycle impact assessment fits into that. Now you might be asking yourself about that 3rd step, that life cycle impact assessment method. Where do these characterization factors come from? Well, when it comes to the assessment of toxic impacts, we typically use nested box models to assess the fate and effects of toxic chemicals. This figure here explains one of the seminal models for life cycle impact assessment called UseTox. The picture doesn't show the very latest version, but it's probably the best place to start for this little lecture. The idea here is that we divide the planet up into rectangular boxes or compartments at different scales. We've got urban, continental, and global scales here. And we consider the air, soil, and the aquatic environments at these scales. An emission into urban air is instantly diluted throughout the urban air compartment. Then it's acted on by natural forces like gravity, causing deposition, and wind, causing advection. All of these forces and more, and other processes like degradation processes, microbial degradation processes, for example, that eliminate the chemical, are taken into account. And this enables us to calculate a concentration of the chemical in each of the relevant compartments. Now, if we know the concentration of a chemical in a compartment, like the urban air compartment, for example, and we know at what concentration it affects people, and we know how many people live in the urban areas, we can make an estimate of the human health impacts the emission causes. Likewise, if we know the concentration at which animals are affected, we can draw conclusions about the impact of an emission on ecological systems. Generally speaking, we make estimates of the loss of species in an area for such toxicological impacts, while for human health we tend to consider cancer and non-cancer effects separately. As I was saying 3 slides ago, life cycle assessment and life cycle impact assessment are about more than toxicity. Having a holistic perspective on the environment means we also have to be interested in climate change, the ozone layer, and other issues. These are generally not assessed with box models like in UseTox, but by a host of other approaches, which we don't have time for today. But one thing that will be apparent at this level of detail is that there are a lot of criteria. You can see 7 on this slide. But remember, I was also talking about technical feasibility and economic feasibility. In other words, what we're trying to do here is rank alternatives using multiple criteria. So this is a segue to my final acronym, multi-criteria decision-aiding. MCDA, or simply MCA, that's multi-criteria analysis, is a whole field of research and applications in itself. So naturally, there are very many ways to do MCDA. My first PhD student, Hazel Rowley, wrote a very pedagogical paper on this topic, so I recommend having a look at that if you want an introduction in more detail than this 2 slides I'm going to show you. This figure is taken from that paper. It's a sort of systematology of MCDA methods. Most people will think of explicit aggregation methods if they know something about MCDA. More on that in a minute. But there are other methods you can use if you're able to interact with a relevant stakeholder group all the way through an MCDA, so-called interactive approaches. Then there are also elementary approaches which apply simple cutoffs to filter a field of alternatives. The explicit aggregation approaches, on the other hand, are all about calculating some kind of final score for each alternative. One of the most popular goes under the acronym of MAUT, Multi-Attribute Utility Theory. Basically, you scale each of the individual criteria in MAUT so that they are comparable, and then calculate a weighted sum using the formula shown here. It's possibly the simplest looking MCDA tool you'll ever use, but it has its problems, like how to deal with non-numerical inputs and how to scale partial utilities appropriately. The other big family of methods tries to avoid these problems by pairwise comparison of alternatives. If you like, each time alternative A beats alternative B, a flow of preferences is directed towards it, and you add up these preference flows. One of my favourites amongst these is called Electra. I don't have time to explain the maths today, so I just put the main equations of Electra on this slide to give you a first impression. Mathematically, it looks a bit more complicated. There are ifs and thens, and you get to have more large operators in the formula than you do with MAUT. But synthesizing preference relations won't kill you. It's just algebra. The outputs of such methods are exemplified on this slide. This is a case study by a PhD candidate, Xi Zheng, whom I co-supervised with colleagues from Chalmers University and NGI in Oslo. What we were trying to do was to pick the least worst flame retardant chemical based on the parent compounds and their worst transformation byproducts. The heat map here on the left shows the 17 flame retardants and indicates in red where a hazard criterion has been met. Orange and yellow indicate high and moderate hazard levels, and green indicates that the chemical has properties corresponding to a safe level. What's nice about this method is you get to see a lot of information without aggregation. It's up to you then to pick what looks best. One of the problems with this is that you're blind to edge effects with this heat map. If the performance of a compound is extremely good or extremely poor within a color class, you don't know. Also, so many colored boxes are there, so many boxes to look at that two viewers might get different conclusions from looking at the same table. So there's an argument for some sort of aggregation method here. That's why we also used MAUT and Electra to process this data and rank the alternatives. Happily, there seems to be an overall agreement that DecaBDE is the worst amongst them, but there was some disagreement about whether MEH TEBP or melamine, which is called MA here, was the least worst. So I've been talking about three acronyms here: Chemical Alternatives Assessment, Multi-Criteria Decisionating, and Life Cycle Impact Assessment. Each of these is very useful tools. None of them is adequate of itself, but each of them can help us understand what we need to do to create a toxicologically safe environment for us and for nature. CAA, it's one of its strengths, at least in theory, is that it's very comprehensive. It takes many different criteria into account and therefore can avoid regrettable substitution. Of course, the downside of anything that fits that description is that it requires a lot of input data, and that makes it slow. This is partly why we're looking for processes like the essential use concept to act as a pre-filter and speed up the elimination of hazardous substances. MCDA avoids the pitfalls of monetization. I suppose the point here is that one of the key alternatives to MCDA would be cost-benefit analysis, but something you can't calculate a cost or a benefit for will fall outside of such an assessment. And if you try to monetize things like environmental health or human health, you can run into a lot of ethical and intellectual difficulties. So we can avoid some of that with multi-criteria decisionating. It's also possible to engage with people in an MCDA process, for example, in the setting of weights for different categories. And the more you engage with people, hopefully the more trust you can engender in relationships that have to decide the future of our industrial systems. The flip side here is that there may be questions of who ought to be engaged in these processes, who ought to be setting the weights, and that's potentially a controversial question. Likewise, the issue of compensation. So, for example, if you've got an alternative that has good performance, maybe above average performance in 5 out of 6 criteria, but is appalling in the 6th, it could very well be the first ranked alternative in an MCDA process if you use certain methods that allow that. There are methods like Electra that try and prevent that. So this is one of the issues we need to deal with in MCDA. Lifecycle impact assessment is a process which enables us to look at a lot of different chemicals in a lot of different situations over the whole life cycle. So in theory, it's much faster than doing a quantitative chemical risk assessment. for similar kinds of systems. It's effectively a pre-made environmental fate and effect model for the average user. A lot of work goes into making those models in academia and elsewhere, but once created, that's relatively quick. The downsides include the fact that a lot of people might confuse it with QRA. I've been in stakeholder meetings where the difference between understanding thresholds in quantitative risk assessment and expected effects in life cycle impact assessment have created difficulties for some of the recipients of the information. There's also the question of which kinds of endpoints ought to be included in the impact assessment we do in LCIA. There's more we could say about that, but just to keep it brief, more generally then, data supply, as with CAA, is a big issue here because life cycle assessment chews through a lot of data. So this can take us a fair while to produce. If you want to learn more about any of these methods, these 5 papers here would be my top recommendations for further reading. And if you have any difficulty getting hold of them, feel free to contact me. Finally, I'd just like to acknowledge all the other partners in this process, and also to thank the EU for its generous funding of this program.
ZeroPM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement number 101036756.